Ion propulsion, also called ion drive, is an advanced technology that has the potential to revolutionize the way we explore space. Essentially, ion propulsion is a method whereby a gas, generally xenon, is electrically charged, ionized, to produce ions. These ions are then accelerated and discharged from the engine, generating the thrust necessary to propel the spacecraft. It's a vital area of research and development that could significantly impact the future of space travel. The concept of ion propulsion was initially crafted by Dr. Robert H. Goddard, a renowned American physicist, in 1906. However, it was only in the 1950s that the theory began to be practically applied. NASA began promoting the technology in the 1960s, resulting in technology demonstrations like the Space Electric Rocket Test 1, SERT-1, which successfully proved the feasibility of ion propulsion. Over the ensuing decades, space agencies and private aerospace companies worldwide have continued to explore and develop the technology. The Dawn spacecraft, NASA's notable mission, tremendously underscored the value of ion propulsion in space exploration. Launched in 2007, Dawn used ion propulsion to travel to and orbit Vesta and Ceres in the asteroid belt. The spacecraft's ion engine allowed it to change its course without excessive fuel use, enabling it to visit multiple targets, an incredulous feat that would not have been viable with traditional chemical propulsion. Overall, the primary advantage of ion propulsion is efficiency. Unlike conventional chemical propulsion, which generates small amounts of high-speed thrust, ion propulsion produces a continuous, though incredibly low, thrust over a more extended period. This slow and consistent production of energy allows the spacecraft to accumulate high speeds over time while using a significantly less amount of fuel. For long-duration missions, such as those to Mars or other planets, this kind of efficiency is invaluable. In addition to efficiency, another significant edge of ion propulsion is its longevity. Since it involves the emission of charged particles, wear and tear on the engine parts are minimal, thus improving the lifespan of the spacecraft and mitigating the risk of failure over longer periods. However, ion propulsion also comes with limitations. One of the key challenges is the small amount of thrust produced, which makes this type of propulsion unsuitable for launching spacecraft from Earth's surface. Ion propulsion thrusters can only function effectively in the vacuum of space, as they rely on prolonged operation to gradually build up high speeds. This restriction implies that other launch techniques like traditional chemical rockets are still required to initially get the spacecraft into space. There is also the issue of providing the electricity required to ionize the xenon gas and accelerate it from the engine. This electricity typically comes from solar panels, but the farther a spacecraft travels from the sun, the less effective these solar panels become. As a result, beyond a certain distance, nuclear power becomes a necessity, which carries its own set of technological and regulatory challenges. All things considered, ion propulsion holds massive promise for the future of space exploration. Despite some limitations and challenges, its benefits in fuel efficiency and lifespan outnumber the negatives. Research advancements continue at full pace to mitigate the remaining obstacles, like the power source problem, and to enhance the utility of ion propulsion. The hope is that this technology will ultimately lead to more extensive, more efficient, and more cost-effective exploration of our solar system and beyond. In conclusion, ion propulsion may not only alter our capabilities in space but also our understanding of it.